It's a great pleasure to be here. Thanks for warm invitation, and it's great to see all these many familiar faces. And for those of you who know me, you probably know that my idea of a happy and constructive seminar is an angry mob, all of you, who is not letting speaker finish. Right. So if this is, you know, if you've been pretending for 10 years that you're this quiet, nice, polite person, and, you know, this is your time to come up. Okay. So let's just have a conversation. So first, I'll start from stating the obvious. Biomedicine is becoming an information science, and information comes from multiple scales. And we, of course, have molecular scale with all the omics research. And an MR signal is coming from there originally. And then the resolution is what we're used with medical imaging, whether it's MRI or anything else. And this is the scale that I want to talk about for the most part. It's this intermediate, I call, as a condensed metaphysicist, I call it a mesoscopic scale because it's in between, or people in diffusion MRI field usually call it a microstructural scale because it's a micron level structure. And that is basically the scale commensurate with cell dimensions. That's where all the enormous tissue complexity happens. That would make tissues functionally different from each other. And that's where pathology and physiology happens. And this is what we want to access, right? But there is no way you can image it directly, unfortunately. You cannot just buy a scanner that would image you this. So can we think ourselves out of this problem if we cannot buy ourselves out of this problem? That's kind of the motivation behind all this. And so basically, you know, I will be talking about this mostly approaching from the modeling perspective indirectly. And then if I have some time in the end, I'll try to show you how we can sort of approach it from sort of brute force resolution improvement, although you guys are really champions in this field. So why diffusion? So this is a structural MRI with millimeter resolution. That's as much as you can do. What we want is, you know, 1,000 times smaller scale. And this is how it looks. And the water molecule over the echo times we typically use in our measurements can probe this much. It's up to scales about 5 micron by 5 micron cut. And so this is the typical diffusion length from a few microns to a few tens of microns. It's a gift of nature. We need to really appreciate that the water diffusion coefficient is such that it's a gift of nature, that combination of water diffusion coefficient and the NMR echo times available to us give us this scale. It could have been much worse, okay? So we can indirectly probe, even though we measure like huge voxels, we can probe this dimension. So it's kind of an in vivo microscope, but it's kind of bizarre microscope because it's so non-trivial to interpret the results, right? And that takes a lot of science to actually do. So if we have our MRI signal, what do we do? We can, and you've heard all these names before, we can just represent it. We can just take it, we can calculate diffusion tensor and parameters of that, FA, MD, etc. You can do Kurtosis tensor. You can do multi-exponential fit, which is just a Laplace transform. You can use any basis. So that's not, to me, modeling. It's a representing, kind of a compressing the signal. There is no physical assumptions here. This talk is about modeling. And modeling is not the formulas. First and foremost, models are pictures. So if we want to understand the nature of microstructural content of the signal, we need to learn how to draw these pictures in the most appropriate and parsimonious way. And that is where kind of connection with the condensed metaphysics comes in. So model is a simplified sketch, but you know, it's not a simplified sketch of just in sense of just minimizing some root mean square. I mean, this sketch, model 1, is probably better in some silly root mean square sense approximation of reality than this. But of course, the model 2 is the true model of reality because reality is a portrait of a person, right? And so if you know that it's a portrait, you know what to look for. And that's really the essence of modeling. It's not the best fit. It's what are the relevant degrees of freedom are. And this is really the talk about how to look for those for those relevant degrees of freedom. And the real challenge, because we're dealing with such an immense complexity, is what to include in our models and what to leave out. So the recipe as a physicist, the recipe to me is to drive the measurement into some maybe hard to get, but important asymptotic regimes where different models with different assumptions would yield distinct functional forms. And that would allow you to select the models, not by goodness of fit somewhere where all models kind of give you the same, but where you really know what the assumptions are and you can really distinguish them. And so I'll show you examples about varying the diffusion time, varying the Q vector diffusion weighting, and if I have time, also the denoising is also kind of, it's a test of the quality. So to sharpen the question, we want model tissue microstructure. That's kind of the premise of microstructural mapping, the field that has been growing and growing and growing within MRI. But I asked my favorite question, you know, without even modeling, can we even distinguish between these two tissues? Like if I give you two tissues, putting them in the scanner, and you measure, I don't know, DTI, measure diffusion, I can easily get you a voxel in a muscle and a voxel in white matter, which will have the same, say it's a fiber, so it's anisotropic diffusion, it will have the same diffusion tensor eigenvalues, the same FA, the same everything. Like, this is the quintessential problem we deal with. If we cannot, in our measurement, distinguish between the two vials of two different tissues, which are so functionally different, what kind of hope do we have to model pathology, to predict disease? So the real question is how, if it's even possible to distinguish these things, right? So if we cannot do this, a physicist in me says, well, then we need to go to the toy model and invent the simplest possible toy model, which is already has the non-trivial properties, and see if we can, what it takes to distinguish between, say, these two random media. So I created, this is the simplest possible sort of mock-up tissue, one-dimensional diffusion, where I put randomly barriers, which are identical and permeable with the same concentration, right? And these are the two samples, green and blue. They kind of look random. Question to you: do they look random in the same way? Do they come from a same sort of probability distribution, or not? How many of you think that they're fundamentally the same, just different realizations of the same random process? No? How many of you think that they're different? Okay. Okay. The majority thinks that they're different. You're actually right. But so this, maybe some of you heard this before. Here's two more examples, and here you see that they're really different. But the point is that if you just measure the diffusion coefficient at time 0, where none of the water molecules hit any barriers, it would be free diffusion coefficient would be the same. If you measure it at a very long time, it will also be the same because the barrier density is the same, and that determines completely in one dimension the long time diffusion coefficient. So there is something in between that may change, and that's the question what. But before going into diffusion, I can ask myself, how do I distinguish between these two samples as a physicist, just looking at the structure? And the way to distinguish different random structures is to look at density correlation function. Or density correlation function, if you transform it, it basically becomes a power spectrum, which is essentially a Fourier absolute value squared of the Fourier transform of the density. So you basically have a density set of delta functions, the Fourier transform absolute value squared. And what we want to look, so those are the colors corresponding to these lines, and you see that they're very different. And what we are really seeing is that at very high K, they're kind of the same. At high K means short distances, where you only probe the structure of a barrier. But they're very different at low K, which is large distances. And this object basically tells you essentially what is the energy of a fluctuation if in a window around K, right? So the smaller the K, the larger the window. And you see that the samples have very different statistics of fluctuations of their density. And you see, for instance, that the red one is completely periodic, right? So there is no fluctuations at low K, and then you see these bright peaks, this basically diffraction pattern. And then, the blue one is actually just a Poissonian kind of short-range disorder. I put them completely in kind of uncorrelated way. And so you see that there is a plateau at small K, and that's kind of like a delta function in R. It's like there is basically no memory in knowing if I'm on this barrier, I don't really know where the next one is, no correlations. And those are kind of two polar opposites. And then there are other things. So for instance, the green one is special because I took the red ones and just shifted each of them independently by a small random, by a certain random amount that I took from some reasonable probability distribution. So I kind of shifted each of them randomly, but because they originated from a lattice, they still remember their origin. So you don't see it locally. Locally, they look the same randomly as blue, but on the larger scale, you can see that the statistics, the variance of the number of them within a window wouldn't grow nearly as much with the window because they still kind of remember about the periodic origin. And so that actually is illustrated by suppressed structural fluctuations, right? The green goes as K squared. Actually, it's an exact result. So and the magenta is I took some intervals distributed by a fat Levy tail, and that gives you huge fluctuations, and so this power spectrum actually diverges, sorry, at low K. So those are very different objects for a physicist, but from the point of diffusion, and that's really the connection, the statement that I want to make is the following. If you actually look at the time dependence of diffusion coefficient, so I told you that at time 0 and at time infinity, all these samples give you exact same result. But if I look at the time dependence, in fact, at the approach of the time-dependent diffusion coefficient to the long time limit, this approach happens qualitatively differently in 4 different samples. And that's a non-trivial result. So basically, I can characterize, so the theorem that we proved in this PNAS paper 2014 is the following, that if I define this instantaneous diffusion coefficient, for those who do diffusion, we usually divide x squared by time. I actually suggest to differentiate because that actually gives you the instantaneous rate of change of mean square displacement. So this is slightly unconventional time-dependent diffusion coefficient definition, but that's more physically relevant. And so you approach long time limit from above as an inverse power law. And this inverse power law exponent, theta, is related to this structural exponent, p, which defines how my power spectrum scales at low K, so 2, 0, etc. And dimensionality of space, which just happens to be 1 here in this example, but it can be arbitrary. So you can see that, for instance, if I look at p equals to 0, Poissonian, p equals to 0 plus 1 divided by 2, it's times to minus 1/2. If it's this green one, it's called hyperuniform disorder, which is almost uniform because it comes from the shifting of the uniform density. Then it's 2 plus 1 divided by 2 gives you 3/2, and so on. If any periodic sampling actually gives you this pathological limit where it's actually exponentially fast approaching to the long time limit, and so on, right? So it's not just a numerical thing. Our postdoc actually created a number of phantoms with permeable films and actually studied the structure function and so did the stimulated echo diffusion measurement. I actually saw it. We just published it in PhysRef. And let me basically tell you now why this relation is such. I'm not going to derive it, but qualitatively, think about diffusion as a coarse-graining process. Think about if you let spins diffuse over some time t, it means that they go over root mean square displacement of some diffusion length. And over this diffusion length, the properties of medium is kind of averaged, right, in coarse-grained. So the longer you let them diffuse, the bigger the window of this kind of Gaussian filter is on the microstructure. And if I just apply the Gaussian filter to these barriers, you'll see, maybe if you squint, you'll see how uniform the red becomes very fast, right? When you increase the filter window. And, you know, the green is obviously more uniform than the blue, and this guy is really wildly fluctuating. So basically, when we increase the diffusion lengths, we suppress the contributions of high K and really focus on low K behavior of the density-density correlation function, which is giving you distinction between different classes of spatial organization. And that's really the key connection between transport, diffusion, and structure, which we want to study. Yeah? Yes?
Either the ability to choose having ambiguity, differences, and permeability barriers.
Yeah, so that's a great question. Suppose I have periodic barriers, but I have random permeability values. It will look like a random, say, Poissonian if you put them uncorrelatedly differently. It will map onto the Poissonian onto this blue sample. Yes. So essentially, what matters. That's a great question. What matters if you coarse grain, right? You forget about individual barriers. You think in terms of sort of what are the local coarse grain diffusion coefficient of this domain, of the size of diffusion length, and what is the statistics of spatial distribution of this local diffusivities. You should start thinking in terms of some kind of diffusion coefficient locally as a function of x, of position. And whether it's made by periodic barriers with random permeabilities or randomly placed barriers with the same permeability, you don't even know. You only see the coarse-grained medium. Yeah, that's a great question. And in fact, you can then start classifying different types of randomness according to this power law behavior of the correlation function. So you can have, so I said, the question is how to draw sketches correctly. Well, so we can have very complex on the very short scale samples, but they can look on the large scale as say this short range disorder sample in any dimension or periodic in any dimension. Or you can come up with actually, now that I started to think about it, you can say, well, okay, there could be a class of randomness which is randomly placed planes or hyperplanes or lines. And they actually give me this 1 over k to some power correlation functions that have this distinct power law exponents. And there are like finite number of this classes of randomness can come up with. Of course, this is not an exhaustive list, but I was filling these holes. Actually, this Nature Physics paper is basically, it was introducing this random barrier class of randomness and diffusion in that. So it's kind of like a 4-man's periodic table of classifying different types of disorder. And the point, of course, is that there is a connection between disorder classes and the dynamics. And typically you see that the stronger the fluctuations, the smaller this power law, smaller this P, it can be even negative if fluctuations are diverging, and the smaller is power law theta. So the slower is the approach to long time limit. It's qualitatively understood because the bigger the fluctuations, the longer you have to sample to get a correct representation of them. Okay? So, yeah, please. Yes.
So I have a related question here.
Yes.
So you say you can or you cannot distinguish between these two situations of having random permeability at every barrier or random distribution?
In the tail, no. Because they look the same from the point of coarse-grained properties. So yes. So in a way, yeah, I can say yes. The structure is periodic, but if properties are random, then it behaves like a random structure.
It's adamant to this question that like you have different types of waters in the tissue, like almost free water that just is limited by barriers, but water which tightly interacts with proteins or other macromolecules, which is almost has a very long resident time.
Yes.
It can be like almost infinite.
Well, so
it can stay for milliseconds on a protein before it moves. So before this,
so
like an infinite like would be.
Yeah, so the real tissues are complex, and you may have different partial volume, different kinds of water molecules that experience very different environments. So then you can ask which power law tail will survive. It's usually the slowest one that will define your time dependence at long times. So you cannot get everything you want, but you can get at least something, and I'll give you all the examples essentially. So basically the take-home message from this kind of theory introduction, and we'll go into applications pretty soon, that media can be structurally disordered in a few distinct ways, and this coarse-graining by diffusion, it looks qualitatively different, and so we can relate the structure universality classes to diffusive dynamics, and measuring the diffusive dynamics is the way to interrogate the system. I measure the power law exponent. Oh, okay, it tells me what class of randomness, what should I model? The point of modeling is always people are worried about how I model. And the real question is what to model. And that is really kind of what I want to focus on. And so the idea of this, the way of thinking about these things is not new. It comes from theory of critical phenomena in condensed matter physics or in statistical physics, where people long realized that there are millions of Hamiltonians you can write, but at a phase transition, they all can be lumped into like handful of universality classes. There is a phase transition, like first order phase transition, second order phase transition, right? And there are different kinds of second order phase transition that are characterized by different dynamic exponents, critical exponents of specific heat, and correlation function scaling at long distances and so on. But there are a very small number of these classes. So it was really a feat of theoretical physics of the 20th century to reduce all this untractable complexity to a very few systems that you can study to death, understand everything, and then say, this behaves like an Ising model. Right? And so essentially, this is a kind of, again, a poor man's version of this, because here the problem is easier, because there is no dynamics of this disorder. The disorder is frozen. The only thing that is moving is our diffusion particles, which are just probing the structure. So, okay. So let's now apply this intuition to the original question. So can we distinguish a muscle from a white matter fiber? So qualitatively, I can apply this Gaussian filter to the samples. And what do I see? The bigger the filter window, the less details I look at, and the more I can see very apparent differences in large-scale organization. Right? I wouldn't think about them if I look at this. I don't know what to look at. Too much information. Now I know that those are kind of random placed blobs, where this thing you see there are these lines, which you wouldn't think about. I didn't think about it when I saw the muscle first. This has really helped me to understand it better. So even like larger filter window, you see still kind of uncorrelated and some correlations. And if I actually do the radially average density correlation function in K space, I see that this muscle gives you 1/k divergence, and that's because of the streaks. Really, if you just take random lines, do this, you'll get 1/k line, whereas the white matter fiber eventually goes to some constant, which is basically means that you have short range disorder. Beyond a certain distance, you have no memory of placing another axon. Right? So these are two different types of randomness. So maybe we have a chance to distinguish between them. So we can make a prediction, right? So according to this simple formula, I predict that in 2 dimensions, -1 + 2 divided by 2 will be 1/2. And this is the muscle data, stimulated echo diffusion data acquired by Jim Kim in 2004. I plot it as a function of 1/√* of time. And so time grows from right to left. And essentially, asymptotically, of course, not for all times, but for sufficiently long times, it becomes kind of a straight line. And this is the heart muscle, where fibers are smaller, so this regime happens earlier. And this is tongue of a cow, essentially. And their muscles are bigger, and so you need to wait longer to get into asymptotic region. So for the brain, white matter transverse to the fiber, P is 0, short range disorder. 0 + 2 divided by 2 is 1. So prediction is power law 1. And this is a beautiful paper by Sharon Partnoy, Greg Steinich, and Steve Blackman, oscillating gradient measurement of diffusion transverse to fiber in CA1 region in hippocampus. And you see, well, this is oscillating gradient, so it's a function of frequency, which is inverse time. So you see this power law 1. linear scaling with omega. I'll comment a bit more on this. So basically, at least fundamentally, these samples are distinct by different classes of randomness, even though they're two-dimensional. Yes?
Is that ex vivo data?
Yes, this is ex vivo data on 20 Tesla or something. Yeah, it's a very beautiful experiment. So now let's go to different organs and tissues and quantify the dynamical exponents. So if we started from muscle, let's continue. This is this data Gene has in his lab essentially done recently validation on a mouse, where also it was a mouse leg, muscle fiber in the leg transverse to the leg. You see the transverse diffusion tensor eigenvalues really go down, whereas parallel kind of doesn't change much. And the transverse diffusion eigenvalues show this time to the -1/2 behaviors. So again, this is a validation now in a mouse muscle of the functional form that selects your universality class of random barriers, random membranes. And this is unpublished. Our student Greg Limbersky recently processed the data of 14 people. Different colors correspond to different muscle group of a human calf muscle. And you see that again, asymptotically, you are in time to the -1/2 regime. Okay? So yes, in parameters. So in coefficients. And I'll show you. So yes, so to get to that, you need a model that works not in an asymptotic regime, but everywhere. And so that's a different task. So now I know what to model, and now I can say, okay, so I can apply scattering theory approaches to, study the scattering of a single membrane, and then use renormalization, solve the Dyson's equation to find the scattering vertex of a single membrane directly, and then use a renormalization group to sum up over multiple scattering of many membranes, and actually get the time-dependent diffusion for all times. And that's published in actually 2011. But you could see this 1/k scaling for the structure function gives you indeed asymptotic behavior diffusion coefficient at one time as time to the -1/2. And Ellspermann did the very high precision Monte Carlo simulations, and red and blue are theory versus Monte Carlo for a range of permeabilities, and they agree pretty well over like 6 orders of magnitude. So this kind of perturbative treatment using normalization group is actually doing pretty well. So now we have a model for all times, and because of that, to answer this question, so we now actually go to a small patient study where we had people where one leg was immobilized in a cast, so we expect muscle atrophy, and indeed different muscle groups atrophy differently, but basically those are control leg, they're always larger myofibers than in a mobilized leg, about 20% effect after 6 weeks of immobilization. And we can map permeability, doesn't really change, my fiber diameter does change. And then Greg was monitoring the patients in the course of physical therapy where they were making exercises and recovering this. So after 4 or 8 weeks, certain muscle groups were actually matching the control fiber diameter on the contralateral leg, which was healthy. Okay, so this is kind of a validation. And again, the numbers are different, of course, because the muscle groups are different, and they should be. Okay, so actually, interestingly, I don't want to talk much about prostate, but similar things happen in prostate, in the fibromuscular stroma of prostate tissue. Prostate tissue is complex, there are like glands and everything, but the fibromuscular stroma actually behaves like a muscle and also displays this one-vascular time scaling. And from that, you can actually, just very recent work published a few months ago, we can actually get the fiber diameter of about 20 microns and permeability. And so that actually interesting because the previous models of prostate cancer advanced microstructure were always relying on impermeable compartments, and you see that power law will be different and the physics would be actually different. So this is about model selection again. So let's go to white matter. So I already showed you this beautiful example of Sharon Partnoy's data. And now, so this is what we expect. Where is this power law scaling coming from? Well, obviously from extra-axonal space, because that's where water hits, it can go anywhere, but scatters off the myofibers and scatters off them because they're placed randomly, that gives you this power law exponent 1. But what about intra-axonal water? It doesn't go anywhere. This theory doesn't apply. But in intrafibral water, completely confined diffusion is solvable easily. And so for oscillating gradients, you actually, it's an exact result, but the expansion starts from omega squared. So for low frequencies, going back to your question, there are different types of water molecules. In this case, there are water molecules inside impermeable fibers and outside. They have different power law scalings, in this case, as a function of oscillating gradient frequency. And now the question is, what would we see? If frequency is small, and we're talking about long time small frequencies compared to the sizes, because fibers are 1 micron diameter roughly, so it's very difficult to go to millisecond diffusion time, right? Kilohertz oscillating gradients, really hard to experiment. So our, essentially you see it's a fraction of kilohertz here. So all our time scales are kind of long on the natural time scale, right? And so if you have a choice, if you have a weighted sum between contribution of omega and omega squared at low frequency, the small number to the first power will completely overwhelm the small number to the second power. And that is why you don't see any parabola here at all. There is a contribution from intra-axonal water. It's just completely overshadowed by this linear piece. And actually the same qualitatively happens if you were to do it in time domain. Probing axonal diameter as a function of time, where now it's a different story. It's logarithmic singularity versus 1 over time, but it's still numerically true that extra-axonal water contribution completely overshadows intra-axonal. And that's why when we want to probe axonal diameters, inner diameters is actually very hard, because extracellular space gives you a dominant effect. And that was kind of a big part of the confusion of the field, where people were getting axonal diameters of like 10 microns, which doesn't happen in nature, in human or mouse brain. And that's because it has nothing to do with inner axonal diameters. The physics comes from a different compartment. And that's how you see this. And yes?
You said the omega square result is exact.
Any confined geometry, any diffusion within any sphere, cylinder, whatever, confined, the oscillating gradient diffusion coefficient frequency at zero frequency is 0, because at long time diffusion coefficient is 0 in the confined domain, right? But its Taylor expansion on frequency starts with omega squared. I mean, the coefficient will have something to do with this diameter of this thing and so on, but the functional dependence is omega squared. Okay, and now it has been also seen by other groups in numerical simulation, etc. So this is basically, if we have a not super strong diffusion weighting, we essentially measuring properties of extra-axonal space rather than intra-axonal space in the so-called axonal diameter map. Okay, and so now let me go to course.
So that 20 micrometers is probably just how tightly the fibers are packed, right? The distance between neighboring fibers.
Here it's about micron.
Yeah, but you said that the 20 microsecond is actually not it's a wrong measure of the intra-axonal diameter. 20
microns.
Yeah,
people were getting 10, 20 microns as axonal diameters, which,
but if you say it's dominated by the extra-axonal water,
yes,
it's actually a reflection of what's the distance between two neighboring.
Well, it's actually, then you have to model that. So there are coefficients in front of this. But indeed, roughly speaking, actually, it's true that, let me give you in the time domain or in the frequency domain, the coefficient in front of this term roughly knows basically about the correlation length of your packing of axons. So if they're randomly packed, the correlation length is roughly the outer diameter, maybe 2 outer diameters. You have to define it correctly. But it's a few times more than the inner diameter. And that's enough, I think, to explain all these effects. Yes, because we have G ratio, there's myelin outer diameter is bigger, plus the density correlation time. I mean, they're correlated at the short scale, but become decorrelated in space at the large scale. So we're probing geometry of extra-axonal space, but I think it's actually more exciting because demyelination, axonal loss, glial infiltration, inflammation actually happens from outside, geometrically speaking. So actually, it's probably good news. Maybe we should forget about inner axonal diameters and don't have just a single focus on them, because that has been for a long time the mantra in white matter modeling. Let's actually look about at extra-axonal space, because that's actually maybe even from the pathology point of view gives you more interesting results. So that's kind of where we're today. And now let me go into cortical gray matter. This is my most favorite example. Again, this is actually not our data. This is a beautiful experiment by those Parsons and Gore in 2003. So they now went to gray matter. It's a rat cortical gray matter, large voxel, where they went up to kilohertz and even 1 hertz. Well, half a kilohertz or even 1 kilohertz. So in a rat brain, this is normal rat brain, and this is globally ischemic rat brain. So clamp the artery and measure 10 minutes after. Basically, poor man's version of stroke, right? And you see that, of course, diffusion coefficient drops at low frequency. That's what we see as a stroke contrast. But the frequency dependence is amazing. Well, first of all, it's there, okay? But secondly, look how singular it is at low frequency. It's like a derivative divergence. It's not like parabola. It's not confined geometry, like it's not omega squared. It's some non-analytic function. And then you think, well, it's completely isotropic system. FA is very low. It's a cortical gray matter. So if it was just completely random, random stuff there, short-range disorder, then in 3 dimensions, short-range disorder in 3 dimensions, 0 plus 3 divided by 2, it would be omega 2 3/2. And omega 2 3/2 would look like a parabola, kind of. But the curvature is completely different, right? This is concave rather than convex. So it's not that at all. It looks like some kind of root, maybe square root. So I just took this data and I replotted as a function of square root of frequency. And this is how it looks. And I mean, I can fit your power law exponent 1/2, which is essentially as exact as you can get. And this is to me as a physicist is an amazing data set, because look, when we study phase transitions, when all these universality classes were discovered by all these people, Landau, Wilson, etc., they were tested on a very well-crafted experimental systems where you drive the system to phase transition and you look at some tiny deviations from the transition temperature and you see power law exponents. Here, it's kind of a dirty biological system. It's a rat, okay? This is a live rat, and this is a dead rat, right? And look at it, everything changed in the life of this rat, right? Life and death. And the ADC dropped, and you know, water molecules, of course, don't maybe care that much that the rat is alive or dead, so you can question, even though there's so much changes in tissue biochemistry, okay, there is some change in parameters, but the power law exponent of diffusion did not change at all. Everything else changed, but one parameter didn't, was this power law exponent. So what is it coming from? This would narrow our search space to understand what changes in stroke, what drives this ADC change in stroke, a 25-year-old question that is still sort of not really resolved. Well, now that I know just a bit of neuroscience, so I know that gray matter is not just a random stuff. It's actually a combination of these neurites, axons and dendrites, which where water, you know, at least maybe 60% or more is inside of those kind of one-dimensional cylinders, lines, and they're not totally straight, and they're not totally perfectly uniform. They have actually all this like beads and structure on them. So if I look at extra neurite water, I will get to the same kind of power law frequency to the first power, similar to the one from the extra-axonal space transfers to the axons. But if I look at one-dimensional diffusion parallel, you know, and assume just the most obvious thing, short-range disorder, then I would get omega to 1/2. That's the same as this blue sample I started from, where short-range disorder gives you times to the -1/2 or omega to +1/2. And of course, now the way to rationalize Mark-Dawes' data is to say, well, there is also an interplay between intra-neurite water and extra-neurite water, but at low frequency, the small parameter to 1/2 will always win over the small parameter to the power 1. That's where all this kind of singular behavior comes from. So that is what we're sensitive to. Okay, so power law exponent allows us to make an educated guess of what changes, what structural changes are most relevant. And lo and behold, I found this papers by Gordon Shepherd, by a very well-known neuroscientist, who actually is counting the statistics of these beads on in this case, I think axons in CA1 hippocampus, and they were basically showing that the variance over the increasing window divided by the mean number in the window approaches some constant, and that's the central limit theorem results that basically means you have short-range disorder, and that universality class is indeed commensurate with what I see in Mark-Dawes' data in diffusion. And more importantly, you see that everything changes in stroke, but universality class doesn't change, so there is no qualitative change in the structure. And but however, you see that diffusivity drops and the slope increases, and those two things are compatible with assuming that the disorder amplitude increases. The disorder amplitude means your long-time diffusion coefficient will drop, but it actually also means theoretically that this coefficient in front of root omega will become stronger, because that kind of comes from the disorder, actual disorder. And so that's kind of again compatible with it.
Also, question here. So,
yes.
Are there some channels, water channels that are called alpha points, which let water communicate?
It's a great question. I'll come to that.
And that in the stroke they are shut down. And
yes. Yeah.
That can lead to such an offset in your two curves there, or?
So if you just have a slow exchange to the lowest order, it won't affect this power loss. That's a non-trivial statement, but you just need to believe me now. I don't have time to explain. But also at this very short times, you know, it looks, we don't know much about the exchange, but presumably at, you know, up to 0.5 kilohertz, it's a few milliseconds, exchange doesn't actually happen in a notable amount. There's this debate what the residence time is, maybe 100 milliseconds or so, but you can roughly think about still water being roughly in one compartment or in the other. So at very low frequencies, you may see something, but it's already a very tiny effect on top of it. But I'll talk about exchange. But okay, so we see that there is a short-range disorder along axons of dendrites. So let's actually see how prevalent is this. So we actually would go to white matter and we study time-dependent diffusion in the white matter parallel to the fibers. Sorry, this was the measurement by Alice Friedmans a couple of years ago. And she sees that stimulated echo diffusion time, there is a notable time dependence along major white matter tracts in humans, up to 500 to 600 milliseconds. And it looks like if I replot it as a function of 1 over square root of time, it's compatible with 1 over square root of time, and again, short-range disorder along the white matter tracts, and I can hack some model and get the correlation lengths of the order of 3-5 microns, and that's remarkably the same as the distance between these very positives that Gordon Shepherd found. Okay, this is human versus mouse. I understand there are different brain regions and on, but this is at least an order of magnitude. And so now we got more interested in this. So we actually have our superstar grad student, Hongxi Li, actually reconstruct the three-dimensional electron microscopy sample in a mouse corpus callosum, and he does the Monte Carlo simulation in this reconstructed sample. So this is just published in Brain Structure and Function. That's the 3D EM. He actually segments myelin and intra-axonal space. Extra-axonal space is hard to segment, it's very shrunk, so we only look at intra-axonal space, over 200 axons that are actually segmented well, and then he can run Monte Carlo simulation along the axons of the length of about 20 microns. And so he also studies the structure, the density correlation function of essentially this irregularities is diameter, and we see that at low k, it's a plateau, so it's a short-range disorder, again compatible with all we know from Goldman Shepherd, and that would give you power law 1/2 in diffusion. So that is the prediction, diffusion, and actually, if you think about it a bit longer, the Kurtosis will also give you 1 square root of time. So this power law exponent is universal, and we expect this to happen. So Homsey does Monte Carlo simulations in all these 200-something axons as a function of obviously diffusion time. This is the time-dependent diffusion. This is time-dependent Kurtosis. It goes up and down, comparable to Dini-Libian's group measurement in red. And this is comparable with what else Freeman saw in humans, at least qualitatively. And then I can replot it as function of 1 square root of time. And I see beautiful 1 square root of time power law behavior in diffusivity and in Kurtosis. And the slope, actually, it's remarkable. You can make a calculation that the slope in front of 1 square root of time in Kurtosis can be completely predicted by this effective median parameters in diffusivity. And this is not a fit, it's actually a prediction. Okay. And then there is a deviation at the long diffusion times of the order of like 80 milliseconds, and that's because of finite size effects, because he makes them periodic, then he wraps them around, right? And then at very long time, the system recalls that it's actually periodic geometry, and the power law changes. It's very cool and sensitive, so you really understand all regimes here. And we did PGIC as well, not to stimulate that, and we see the 1 square root of time in humans. And I mean, of course, we can go only to, what, 20 millisecond diffusion time. I can only dream if conic tone scanner can give us a few milliseconds where maybe this time dependence will flatten, and we can actually see the transition to sort of short range limit and probe much better the statistics and maybe sizes of these beads, because they're actually known to change in pathology, in Alzheimer's and stroke and so on. So that's a kind of, could be maybe a very unique microstructural contrast. So far, diffusion is a coarse-graining. We reveal universality effects in the power law approach to long time limit, and the scalings is an in vivo model validation method to reveal relevant degrees of freedom in the structure, and we see that these random permeable barriers manifest themselves in muscle and in prostate. This short-range disorder in 2 dimensions describes extra-axonal and extra-fibrous diffusion in brain, and uncorrelated short-range disorder in 1 dimension describes transport along the neurites. Okay, so now I can plot this all in my favorite graph, which is parameter space of diffusion. Everybody thinks about b-value, but in reality we have Q, basically space, and time. We should think in terms of this 2D rather than 1D plot. The b-values, contours, lines are drawn like dashed lines here. But in this talk, so far I was looking at increasing diffusion time at low diffusion rating, because I was just looking at diffusion coefficient. And I was basically seeing different time dependencies and Kurtosis as well and so on. But in principle, you can ask yourself, okay, so what happens when you go along the Q-axis? That's actually very non-trivial and interesting as well. It's actually very hard to do at short times at large Qs. So it's kind of more natural to say at long times when each compartment becomes Gaussian, almost Gaussian, let me just go ramp up the diffusion rating at sufficiently long times, maybe 100 milliseconds or so, and just think what happens there. And what happens there is a completely different physics, but it also gives you very interesting scaling laws. So I'll just mention briefly this result that actually goes back, if you read correctly, the paper of Chris Kroenke is already kind of there. So basically, if I look at intra-axonal space, and I suppose that there is no transverse diffusivity, the axonal diameter is negligibly small, one-dimensional sticks, right, with some angular distribution. And what is the diffusion signal? In the Gaussian approximation, it's just e to the minus b value times diffusion coefficient times the cosine squared of the angle between my gradient and the stick orientation. And so if the cosine angle is 1, the angle is 0, that I'm very suppressed very fast. I'm exponentially suppressed. If my angle is 90 degrees, I'm not suppressed at all because I neglected transverse diffusivity. Right? So now I have a distribution of these sticks, and you can see right away that if my gradient is this direction, that sticks, that axons sort of almost transverse to the gradients will be the ones who would contribute to this signal the most, because they're the ones that are least suppressed. And I can estimate what is the kind of it's kind of a pancake in 3 dimensions, right? The distribution. And the width, angular width of the pancake is actually scaling as 1 over square root of b value. Because that's where this exponential, you can just make an estimate, bd times this squared is order 1. And that gives you 1 over square root of bd as this angular size of the axons that are not super strongly suppressed, and that gives you contribution to this integral. So it means that the whole signal will actually scale as 1 over square root of b. And the extracellular signal has diffusivity in every direction, and therefore at large b it will be eventually exponentially suppressed. So if I see 1 over square root of b scaling at super high b, I will know for sure that there's sticks like axons or maybe other processes, and I don't see anything else because everything else will be exponentially suppressed. And so let's actually see. We have a Prisma scanner, so we did that at up to B10,000. That's what experiments measured a couple of years ago. Actually, this is the maybe first measurement on a Prisma up to 10,000. Couldn't go further just because the sequence didn't allow us. There was a signal, of course, even at B10,000. We averaged over all shells, over all directions in each B shell, and basically got this 1 over square root of B. Again, this axis is 1 over square root of B, so B value goes from right to left, increases, and you see that it becomes a symptotically straight line. And then I just, for fun, asked for Chris Kroenke's data of NAA, the intra-axonal compartment, metabolite, and I just rescaled the b-value. I took this data and replotted with rescaling the b-value because the diffusivity of NA is about a factor of 5 slower than in water. Therefore, the effective b-value has to be rescaled from like 30 to like 5 or something. And that's the intra-axonal contribution only, right? Also kind of wants to go to 0 as 1 over square root of b. And so now, obviously, this is the extra-axonal contribution. You can right away read off where it disappears. At B6000 or 7000 roughly or so, there is no extra-axonal contribution. All the scaling you see is from intra-axonal space only, based on non-trivial non-analytic scaling. Okay, so can we go? Yeah, so we published, this is actually published in Neuroimage just a few months ago. And we mapped this power law exponent. It's pretty uniform across all the white matter and practically no intercept, essentially 0. So conic tone, go to higher b values. So Yella Gerard, our postdoc, went to Derek Jones's site, sorry, and asked them, how about let's go up to say B25,000. And they would say, oh, you won't see any signal. And Yella is like, no, there is a theory according to which you will have a signal. I said, no. We never went beyond B7,000. So just because, well, you know, this is B25,000. Or 25 is kind of physics units, microns and milliseconds. There's a lot of signal, as you guys know. And of course, you see it better because of our denoising pipeline, which I mentioned a little bit later. But if I replot the signal as a function of the square root of b, now Prisma was kind of here, and we got this much. And it still kind of looks pretty straight. This is white matter, and this is the gray matter. Okay, the 3 by 3 by 3 voxels, it's hard to segment the human cortex for different subjects, but you can see the difference, right? Do you see any qualitative difference in this behavior? If you look from here, do you see that the curvature is different? This is kind of concave, and this is kind of always convex. So you would rationalize this concavity if you remember that there is some transverse diffusivity that I've neglected, but at such huge b values, I can start to be sensitive to that. That's where the axonal diameters start to manifest themselves at this super high b. And we can convert them using Norman's formula to the actual diameter values. And they're heavily weighted by largest diameters, but we're getting more sensible numbers of the order of 3, 4, but because they're heavily weighted by the tail of the axonal distribution. Whereas the gray matter is always convex. And there are many different reasons why that could be true, but actually we thought about exchange, your question. And if you just take a Karger model with the sticks and some extra stick space, an angular average, you will actually get the next contribution to be positive as a function of b to the minus 3/2, and you get exchange rate in front of this coefficient, and you can sort of estimate it over a few tens of milliseconds. So it's a very noisy estimate. It would be really good to study it much better with high resolution on, again, high performance scanner. And so, but basically now I'm able to fill up all this diagram. So that's where the coarse graining with time, this is this spatial dependence with Q. That's how kind of we can place all our experiment on this. And so just to sort of sum up this part is, what to model is more important than how to model. And modeling is about focusing relevant degrees of freedom, what dominates the signal, not what we might like to see. And using distinction functional form is a great way to select and validate models. Blind fit quality is all very good there, no matter what models you take. It's kind of irrelevant. Almost everything fits, almost nothing is true. And these problems are hard. And so, I don't know, if you give me 2 minutes, I can give you an overview of denoising, which will have some functional forms, right? We started 5 minutes late, so maybe I can. Okay, so let's now switch gears and ask, okay, how can we make voxels as small as we can? Okay, microstructure is great, but that's like infinitely far. Let's just improve resolution. And so you guys all know that what limits MRI resolution is SNR, and essentially it's the voxel volume. Noise level is just noise level in the coils. So that's why, nobody typically in the right mind does the clinical diffusion, say at B2000 with sub-millimeter resolution. Again, people like having who've been pushing the limit, but I specifically choose a very, in-your-face example. TE is 130 milliseconds. No grappa, this is as bad as it gets, okay? And of course, you're not supposed to see anything below 1 millimeter. You already suppressed your signal at 2000 pretty damn well. You're not seeing anything, right? Except, of course, if you do the reconstruction using our noise reduction method based on random matrix theory. So this is the same weighted image after denoising, where we remove the data before the reconstruction. And this is the same data when we do, say, DTI and look at the direction of principal DTI eigenvector. And of course, you're not seeing anything here. This is Siemens seductive combine. And this is, the denoise data set. Kurtosis maps are not that bad and completely useless for regular reconstruction. So the idea is that, if you do principal components analysis in a highly redundant acquisition, then if the kind of matrix that you do the PCA on is large enough, then random matrix theory tells you that there is a universal signature of pure noise contributions to this random matrix. And so the key is to create it correctly using redundancy in coils, Q space points, and voxels. And we can construct sort of from this rank 3 object, rank 2 object in a kind of clever way and denoise all the coils. And then, of course, combine them as you would want to combine them, grappa, etc. If you want to parallel imaging. These are normalized residuals. You're not supposed to see any anatomy because we should make sure we don't remove anatomy. And the whole point of this talk is about functional forms. So this is the Gaussian residuals. So this is a normalized residuals that I bin and plot the histogram in semi-log plot. And I plot log versus residual squared, normalized by sigma squared. So if it's a perfect Gaussian, the straight line with a slope -1/2. And this is, the red dots is actually statistics of residuals in all coils and diffusion weightings. It's perfectly Gaussian down to, you see R squared is 25, down to 5 standard deviations in the tail. It's down to 1 part per million relative to the bulk.
So are you applying this to complex data?
Yes, of course, at each coil complexly. Yes, 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 yes.
I have one question on the comparison. I mean, the denoise coils all use all the diffusion data, right?
Yes.
Wouldn't it be then a more fair comparison to other noisy coils that you average n times as many directions that you have? You know, I mean, just to, because the diffusion analysis kind of averages over multiple images.
Yeah, so but the whole point is to, yes, I understand, but the whole point is to use the whole stack to increase the redundancy. And that's why the results are much better. And not to reconstruct it on
for visual comparison.
So for complex data, the
yeah.
maximum likelihood is
So I'm using, we're using adaptive combine, if that's what you're asking. After we denoise everything at the same time, and then unwind, and then push it through the standard reconstruction plot line as if nothing happened. And just because you removed all the noise, most of the noise, you see how much. So this is a water bottle. You see for free 5 times drop of the Ration floor, basically giving you as much dynamic range in the diffusion measurement. You see how much narrower the distributions of mean diffusivity in different brain regions are, also a factor of 3 or 4.
A lot of that is just complex data.
No. We then take a magnitude. We do the fits on the magnitude images. That's not the point. The point is to do the PCA and with having all the diffusion measurements combined, not on every image separate.
But then what's the typical SNR that you operate on? Because I think in your SNR this difference is...
Well, this is, I mean, I showed you different set of brains. I mean, even very low SNR that you can't see anything, you can recover factor of 4 or 5 in SNR. And look at it this way. This is the white matter in the brain at 2.0 microns, etc., 2.8 microns. Again, this very noisy acquisition was 113 millisecond echo time. And you see that if I up to B5000, on a Prisma, and you see that, you know, at very small voxels, I basically hit the Ration floor right away, don't have any dynamic range, and here I have this kind of 1 over square root of B scaling, even at 0.8 millimeter.
The point is you wouldn't have a reshape for
Yeah, sure, I can stay in the complex phase, yes,
so
yes.
that's
Yeah, okay, sure. But
does that mean the result?
well, it's hard to tell.
no, it's better because there is no Ration flow, but the point here is it's better than to use every image separately. So the point is that the redundancy, if you have the whole Q-space stack, allows you to remove more noise than you otherwise would.
So when you do this, you start with the data from each coil. You take basically a square blob of it across all the different directions.
Yeah.
Do a PCA truncation.
Yeah.
A good way to truncate.
Yeah, I arrange coils, Qs, and voxels in a clever way that I have.
So what's the assumption of that truncation? Why do you pick that truncation? Does the data have to be IID, or what does it have to be?
So I make it IID, rotate it to the basis where it's IID using
So
close
it's IID in noise?
Yes.
Does it
Yes.
has to be IID in signal?
No, of course not. No. And the marching capacitor, random matrix theory will tell you where the cutoff is.
So how do you determine the size of the square that you use for that?
It's
Spatial.
well,
And
it's
how
a
does
trial
that
and error.
affect
It's what we
And how does, when you accelerate, when the voxel folds,
Yeah.
and the face is different for different things?
Yeah. So we unwind
I
faces.
just want to understand.
Yes, so I don't have time. We can talk about it more, but we do. There's some magic that's going on. When wind faces, we make sure that the number of degrees of freedom is as small as possible. Yes, and there is a dependence on the kernel size of this. Anyway, so but you can do fiber tracking again to improve so on. So basically, I would like to thank the group that we established with us a few years ago, and the microstructure review that we published just recently in MRI Biomedicine has basically all this concept that I described, and just the last functional form of this talk the number of publications with MRI and microstructure as a function of years, time, you know, exponentially increases over 2 decades. I don't have an effective theory for this phenomenon, and this is just an observation, but it's observation that's showing how much interest currently is in this field to understand what we're measuring, to understand where the signal comes from. It was order 1 papers per year in the 90s, and it's over 250 now. And based on this interest, trying to harness this enthusiasm, Greg Stanish and I are cordially inviting all of you to attend the first ever Gordon Research Conference in Tissue Microstructure Imaging that we just pushed through Gordon Committee. We're starting it. This is the first meeting right the week after the 4th of July, very close to you guys, Mount Holyoke, a short ride. And the point is, it's not just MRI. It's to connect us to different fields, to learn from them, to make sure they tell us about validation methods that we otherwise maybe don't know, but also to tell them our story. Because I see too often that people from other modalities, from basic biology, neuroscience, might not realize just how much depth there is here it takes to interpret our images. We're not just doing grayscale CT-like images. There is so much physics there. And I think this is the great venue to have this discussion. So please come. Thank you very much for your attention.